Susan is a college student who receives a heavy sweater from her aunt at the first sign of cold weather. Susan has determined that the probability that the sweater is the wrong size is 0.47, the probability that it's a loud color is 0.59, and the probability that it's both the wrong size and a loud color is 0.31. She's probably compiled this from previous experience of her own experience and maybe her relatives, and I don't know. This seems to me like an empirical probability. That's why we don't have a sample space here. We just have the raw probabilities. All right, so let's say find the probability that the sweater is the correct size and not a loud color. Let's define some events here. Because calling it correct size or wrong size, and loud color or not a loud color, yeah, I guess you probably could do it that way, but let's go ahead and and define some events. Now I could go with wrong size being, I don't know, W, the event W. I think C makes more sense as an event. And then if I'm talking about the wrong size, this would actually then be C complement. So the correct size would be C, the wrong size would be C complement. You can see, just like when we're dealing with variables, you want to have as few event names as possible. Let's see. If we say not a loud color, let's go ahead and say a loud color is L. Thus, not a loud color would be L complement. Okay, so from reading this stuff from up above, rather than having to read through all this, I'm just going to compile some of the information. The probability that the sweater is the wrong size is 0.47. C complement equals 0.47. Okay, that's what that says. The probability that it's a loud color is 0.59, so L equals 0.59. And the probability that it's both the wrong size and a loud color, so C complement intersect L, is 0.31. All right. Find the probability that the sweater is the correct size and not a loud color. We're trying to find C intersect L complement. We have C complement intersect L. So we're given kind of bits and pieces. I probably could piece this together using just my union rule and doing stuff like that, but I think since there's so many different bits and pieces of information here, I'm actually going to set up a Venn diagram and talk about all the different events that are happening here. I'll go with events C and L. And I know that C complement intersect L is 0.31. So if you're outside of C, but you're inside of L, C intersect L complement is this region right here. So that region right here is C complement intersect L. We know that that's 0.31 within here. And I could actually use that to find what this region is, because I know that L in its entirety should have a size of 0.59. So let me pull out my calculator. We'll do 0.59 minus 0.31, means that there should be 0.28. That's the probability of the stuff left here, 0.28. All right, I know that C complement is 0.47, so everything outside of C should add up to 0.47. That should be this region and this region. Only one of those is unknown, so that means I can go ahead and say, well, if the sum of them is 0.47, then the one that's on the outside there must be 0.47 minus 0.31. Oops. 0.47 minus 0.31, which gives us 0.16. So that means this area out here must be 0.16. And now I can actually figure out, in total, I haven't really talked about this with Venn diagrams yet, but in total, our universe, well, actually, it's not our universe in this example. This is our sample space. We're not calling it a universal set. We're calling it a sample space when we're dealing with events. We know that in total, the probability of S, well, n of S over n of S. You're taking the size of something divided by itself. It'll have to be 1. So in total, if we were to talk about the total size of the sample space, the total probability of the sample space, all of this should sum up to 1. So that means if I was to take 0.16 plus 0.28 plus 0.31. So far I have 75% of the total area accounted for. That means that this remaining area must be that remaining 25%. Okay, so I'm just filling in a Venn diagram so I can kind of get a better grasp on all this stuff. Now in this question we're being asked to find C intersect L complement. C is the stuff that's inside C. L complement is the stuff that's outside L. So it looks like C intersect L complement is exactly this 0.25 that we just found. Alright, find the probability that the sweater is the correct size or is not loud. So correct size or is not loud. When we're dealing with intersections, we got more restrictive. Remember, so if we're saying C intersect L, you talk about the areas that are overlapping. Or C intersect L complement ended up being this region right here. It was more restrictive. Instead of being C, which was this whole thing, I had to cut this little intersection area out, and I ended up with C intersect L complement is there. With unions, you go the opposite way. You start off with C, and then you add on additional stuff. You would add on this stuff over here. Or no, L complement. You would add on this stuff that's out here. That stuff out there. So C union L complement is everything except for this region. It's all of this stuff. So everything except for this bit here. So in total, you could say, since it's everything except that bit, I could go 1 minus 0.31, just using my complement rule, which would be 0.69. That would be one way of going about it. Or I could say it's going to be 0.16 plus 0.25 plus 0.28. The sum of those three, which should sum up to be the same thing here, 0.16 plus 0.25 plus 0.28, which gives me 0.69.